To measure sound, engineers use a device called a sound level meter. It's essentially a very sophisticated microphone that measures sound pressure and displays it in decibels, or dB. But not all meters are created equal. They come in two main classes, Type 1 and Type 2. A Type 1 meter is a precision instrument. It has a very high degree of accuracy and is used when the results might be part of a legal dispute or require strict scientific rigor. A Type 2 meter is a general-purpose tool. It's still accurate, but has a wider tolerance for error. It's great for initial surveys or situations where you need a good enough measurement without the high cost of a Type 1. Engineers don't just want to know how loud the loudest bang is, they need to understand the character of the sound over time. This is where special metrics come in. One of the most important is LAQT. The L stands for level. A means it's A-weighted to mimic how the human ear hears. AK is for equivalent, and T is the time period. So LAQT is the average sound energy over a specific time, like an hour or a full day. It gives us a single number that represents the steady, continuous noise level that would have the same energy as the fluctuating sounds that actually occurred. It's perfect for assessing the overall noise from something like a busy road. Another key metric is L90. This tells us the sound level that was exceeded for 90% of the measurement time. Think of it as the background noise. It captures the quietest moments, filtering out short, loud events like a passing car or a dog barking. L90 is crucial for understanding the underlying ambient sound of an area. If a new factory is proposed in a very quiet rural area with a low L90, even a moderately noisy operation might feel very intrusive to the residents. Planners use L90 to make sure a new noise source won't completely change the character of a place. To make sure these measurements are reliable and comparable anywhere in the world, engineers follow standards like ISO 1996. This procedure tells them exactly how to do it. The meter must be placed on a tripod, typically 1.2 to 1.5 meters off the ground, and away from any reflective surfaces like walls that could bounce the sound and skew the reading. A windscreen, that fuzzy ball you see on top of microphones, is essential to prevent the sound of wind from ruining the data. The standard also specifies how long to measure for and what weather conditions are acceptable, because rain or high winds can create their own noise. When we talk about air pollution, we often think of smoke. Much of the danger, however, comes from tiny particles we can't even see, called particulate matter, or PM. To measure these, engineers use a clever device called a beta attenuation monitor, or BAM. It works by pulling a known volume of air through a filter tape. At the start, a small, safe source of beta particles, which are just electrons, is aimed at the clean filter paper, and a detector on the other side counts how many get through. Then, as the air is sampled, particulates get stuck on the tape. The process is repeated, but this time, the layer of collected dust blocks some of the beta particles. The detector registers a drop in the count. By measuring how much the beta particle signal is reduced or attenuated, the machine can calculate the mass of the particulates on the filter with incredible precision. Another group of troublemakers in our air are nitrogen oxides, or NOx, which come from burning fuel in cars and power plants. To measure these, we use a method called chemiluminescence. Chemi means chemical, and luminescence means light. The instrument takes an air sample and mixes it with ozone, O3, in a reaction chamber. When a nitrogen oxide molecule, specifically NO, meets an ozone molecule, it gets excited and then releases that extra energy as a tiny flash of light. A very sensitive light detector measures how many flashes are happening per second. The amount of light produced is directly proportional to the concentration of NOx in the air sample. It's a brilliant way to see the unseen. But where do you put these monitors? You can't just place them anywhere. This is where meteorology comes in, especially the wind. Engineers study weather data to create a wind rose, which is a diagram that shows the direction and speed of the wind over a period of time. If a new factory is planned, and the wind rose shows that the wind blows from the west to the east 80% of the time, you wouldn't put your monitor to the west of the factory. You'd place it to the east, downwind, where any potential pollution is most likely to travel. The wind rose is a roadmap for pollution, guiding engineers to the most effective monitoring locations. Understanding meteorology is also vital for interpreting the data you collect. For example, on a day with very little wind, pollutants might get trapped near the ground in a process called an inversion, leading to a high reading. On a windy day, the same amount of pollution might be dispersed quickly, leading to a low reading. Without weather data, an engineer might not know why their numbers are going up and down. By combining air quality data with wind speed, temperature, and rainfall, they can build a complete and accurate picture of what's really happening in the atmosphere. Collecting all this data is great, but it's completely useless if it's not accurate. That's why quality assurance, or QA, and quality control, or QC, are non-negotiable in environmental monitoring. QA is the big picture. It's the overall system and set of rules you put in place to prevent mistakes. It's about having a solid plan. This includes things like writing a standard operating procedure, or SOP, for every task, ensuring all staff are properly trained, and having a clear schedule for equipment maintenance. QA is proactive. It's about designing a system that produces reliable data from the start. QC, on the other hand, is the hands-on part of the process. It's the series of checks you perform while you're doing the work to make sure everything is running correctly. For a sound level meter, a QC check involves using a piston phone or an acoustic calibrator. This is a small device that produces a very precise known sound level, like 94 decibels. Before and after each measurement session, the engineer puts the calibrator on the microphone. If the meter reads 94 decibels, it's working perfectly. If it reads something else, it needs to be adjusted or serviced. This check guarantees that the data collected in the field is trustworthy. For air monitoring equipment, QC is just as rigorous. A BAM unit might have an automatic QC check where it tests itself with a reference membrane of a known density to ensure its beta detector is working right. For a chemiluminescence NOx analyzer, QC involves feeding it SPAN gas, which is a canister of gas, with a certified known concentration of nitrogen oxides. If the machine's reading matches the concentration on the canister's label, you're good to go. They also use zero air, which is a special gas with no pollutants in it, to make sure the machine reads zero when it's supposed to. In the end, all this talk of monitoring, standards, and quality control comes down to one thing: trust. An EIA report can have a huge impact on a community and the environment. Decisions worth millions of dollars and the health of an ecosystem hang in the balance. These decisions must be based on solid, defensible, scientific evidence. By following standardized methods and implementing strict QA and QC protocols, environmental engineers ensure that the data they present is not just a bunch of numbers, but a true and reliable representation of our world. This allows us to build a better future, thoughtfully and scientifically.